On test 4, the problem I had the most trouble with was question 4. Test 1, question 4. The problem was set up so that a spring was connected to a pole in the middle of an air hockey table, and on the other end of the spring was a puck, which is donated by the R vector, which is its position. So in the problem, we pull the spring out with our hand, and then we give it a push with a certain velocity, and the spring goes round and round. 4a asks us to find the net force on the spring, or on the puck. So in order to find that, it's actually, the table is blocking the force of gravity, so the only force acting on the puck is the spring. So let's first start out by expressing the puck's, or the length of the spring, in terms of x and y coordinates. So the length of the spring equals the magnitude of r, which is x naught squared plus y naught squared plus 0 squared. And then the force of the spring is equal to the negative spring coefficient times the length of the spring, or the stretched length of the spring, minus the initial length of the spring, times L hat. L hat is the unit vector of the stretched length of the spring. L hat equals the position vector over the magnitude. In other words, the position vector over L, which equals x naught, y naught, 0 over L. So substituting that back in the spring force equation, equals negative Ks by L minus L naught by the x coordinate of R, or of L naught, over L. The y coordinate is the same thing, and the spring force is the same as the net force, since there are no other forces acting on the puck. This concludes 4a. Second part of question 4, 4b, wants us to figure out the vector momentum after a certain change in time. I have stated the momentum principle, Pf equals Pi plus F net delta t, and Pi is the mass times the initial velocity, which is stated in the setup of the problem, which is mvi, which equals mvx naught, mvy naught, 0. So now substituting our F net in the equation in the momentum principle, Pf equals mv x naught mv y naught, 0 for the initial momentum, plus F net I've already multiplied delta t into Fnet to make the thing simpler, but you could go into several other steps. So once we sum these two up, we get our final momentum. Which comes out to be mv x naught minus ks L minus L naught x naught delta t all over L, comma mv y naught minus ks L minus L naught by y naught by delta t all over L, comma 0, and that is your final velocity, or momentum. Third part of question 4 asks us to find the updated position after delta t seconds. So we can assume the change in time is small, so the average velocity pf, or momentum over mass, is approximately equal to the final momentum over the mass. So continuing on, our initial position, so PRF is going to equal R sub I plus delta t over m by our momentum, which from the previous problem is pretty long, so just refer back to that part of the video to see it. So when we finally substitute everything in, it's going to be x naught, comma y naught, comma 0, plus, I'm going to already factor delta t over m into it, so I'll walk through that too. So the momentum is going, or the new momentum is going to be Vx naught delta t, because you multiply by m, which cancels out the delta t over m, so it's just Vx naught delta t minus ks L minus L naught by x naught all over L, or ML, by delta t squared, comma Vy naught delta t minus ks L minus L naught y naught delta t squared all over ML, and you probably can't see the third component in the video, but it's a 0 still. So finally, after adding these two together, your final position is going to be x naught plus v x naught delta t minus ks L minus L naught x naught delta t squared over ml, comma, y naught plus v y naught delta t minus ks L minus L naught y naught delta t squared all over ml, comma 0. That is your final position for problem 3. Quite long. Part D of problem 4 wants us to find the new force acting on the puck delta t seconds after we release it. So in terms of the problem, we want to call RF, which was our final position from the previous problem, R new, and RF and F, we're trying to find F net comma new. So to start with this, we want to find out the new length. This, which we call L new. This is a huge pain in the butt, but we will do it anyway. So, first, we take the square root or we find the magnitude of R new. So, that is x naught minus v naught delta t, or plus v naught delta t, v x naught delta t, minus ks L minus L naught x naught delta t squared all over ml, quantity squared plus y naught plus v y naught delta t minus ks L minus L naught y naught delta t squared all over ml, quantity squared. And the third component is a 0 squared, but that's 0, so I'm going to leave that out. Now we continue to do this problem. The things are going to get too big, so I'm going to just leave it in vector format. So, in order to find out the force, recall the force of the spring, which is the same comma new, equals negative ks by L minus L naught, or L new minus L naught, by L new hat. So L new hat is going to equal R new over the magnitude of R new, which is also equal to R new over L new. So finally, substituting everything back in the equation, find the F net new equals negative ks by L new minus L naught multiplied by L new hat, which is the same thing as R nu all over L nu. And there we have our final force, which would be about 2 lines if I were to write it out. So that is problem 4.